Alright, here we go with the Chapter 7 homework review. The average score on this was about 9 out of 12, which is pretty typical for this time of year. I suspect there's a little bit of chemistry apathy related to the recent exam, but the scores overall weren't too bad, but there are a few things we need to go over. Some of them were things I either glossed over or didn't cover at all in class, and others were things we just need to sort of reinforce from what we should have learned for this topic. So one thing I didn't really cover in class, and we might see it in future problems, and we'll give you the conversion factors you need if you're going to have to do these. But here we're looking to just convert. So I forgot to write the rest of the problem here, but we want to know what is this value in joules. So we're given a value in calories with a large C, and we want to figure out the value in joules. So we didn't talk about the unit calories. It's not really covered in your book, but it's one we should become familiar with. So calories are a little bit confusing because there's two units that have the same word, they just have different capitalization. So one lowercase c calorie, it's the amount of heat required to raise 1 gram of water in temperature by 1 degree Celsius. So that means 1 calorie is equal to 4.184 joules. This is the key conversion factor. So we remember that the heat capacity for water is 4.184 joules per gram degree Celsius, which means it's 1 calorie per gram degree Celsius. So calorie is a convenient unit because the heat capacity of water is exactly 1. But what's a little bit confusing about calories is that if we have 1 kilocalorie, which is 1,000 calories, that's equal to 1 calorie with a big C, and that unit is used especially in the context of nutrition. So when you read a food label and it says, this food has 500 calories, you're talking about calories with a large C, an uppercase C, and that means 500 kcals or kilocalories of energy. So these are the conversion factors we need. So if we're going to convert 4.1 times 10 to the third calories into joules, what we need to do is first convert that into calories. So we have 4.1 times 10 to the third calories with a big C. That's going to be equal to 1 kilocalorie, so we can use this trivial conversion factor to get into kilocalories. And then we have 1,000 calories per kcal. And then finally we can go into joules, 4.184 joules per calorie. So that gets us into the units we want, which is joules, and we should get, I believe it's 1.7 times 10 to the 7. Yep. So 1.7 times 10 to the 7th joules. Now this was a multiple choice question and none of the answers matched this. You would have wanted to pick none of the above for this one. Okay, but it's 1.7 times 10 to the 7, and that's the conversion we use. So the one that you should become familiar with, and we'll probably give it to you if you need it, but it's one you'll see sometimes, is this one here, calories into joules. Alright, so that takes care of that one. Now another type of problem we saw, and we talked about this early in the week last week, is expansion compression work. So here we have a gas, and it's either going to expand against a constant external pressure or it's going to be compressed by a constant external pressure. And the equation for this is pretty simple, but we do have to remember there's a negative sign in it. So work for expansion or compression is the negative of the external pressure times the change in volume. So we need to remember this negative sign here. This is important, or else we won't get the sign correct. And many of you that got this problem wrong just picked the one with the wrong sign. You had the magnitude correct, but the sign was wrong. So when we do this, we have to calculate delta V. So delta V is the final volume minus the initial volume. Write that correct. So we have to look at the problem here, and we're compressing the gas. So when you're compressing something, you're decreasing the volume, which means delta V should be negative. So as it says here, we're going from 35 to 4. So our final volume is 4 liters, and then our initial volume is 35 liters. So it's also important to get the sign for delta V correct. We get minus 31.0 liters. So the work in this case is going to be the negative of the external pressure, which is 9 atmospheres, and then delta V is also negative, So when we multiply these out, we get 279 liters atmospheres. Another thing with this types of problems is you need to look at units closely. So we're multiplying atmospheres times liters, so our unit is liter atmospheres. This is not a standard unit for work, so we need to convert this into joules, as all the answers in the problem I believe are in joules. So once we do this, the work in joules is going to be 279 liter atmospheres, and then the conversion is 101.3 joules per liter atmosphere. So we get 2.8 times 10 to the 4th joules. Okay, so it should be positive because we're compressing the gas. Anytime we're doing a compression, work should be positive. We have to remember to convert into the correct units as well at the end. And then this problem here, calculating delta E using Q and W, or heat and work, takes it one step further. So we learned that the change in internal energy for a system is equal to Q plus W. So it's heat plus work. It's a very simple equation, but we need to take into account the signs yet again. The sign convention is perhaps the most difficult part. So we have to read the problem to get the sign. So we're given two positive numbers. That doesn't necessarily mean that the mathematical quantities of Q and W are positive, because if we look at the problem here, it receives 256 joules of heat. So translating that would tell us that Q is equal to plus 256. So if the system receives heat or absorbs heat, or whatever word is used there, Q has to be positive. But then we're told that it delivers 983 joules of work. So if the system is doing work or delivering work, as it says here, that means that the work is going to be negative. That's going to contribute to decreasing the internal energy. So we have to be aware of the different terminology that is used in describing heat and work in a word context. So if we're receiving heat or work, or the system has work done on it or heat given to it, those are all positive. If the system releases heat or loses heat or does work or delivers work, if it's flowing out, then those are going to be negative numbers. Alright, so when we put those in, then we get a 256 joules plus minus 983 joules. So overall we're going to get a negative delta E for this process. So it's absorbing some heat, but it's doing more work, so overall the delta E is negative. Okay, so that's how that one works. Pretty simple equation, just get the signs correct, as we talked about in class. So the next couple we're going to do in this review are calorimetry problems, and there's two things we can use a calorimeter for. One is to determine heat capacity of an unknown object, and the other is to determine the change in energy or the change in enthalpy for a chemical reaction. So we'll do the first of those here, determining heat capacities. Now before I start, I'm a little bit loose with terminology, as most people are, but there is a small difference we should be aware of. So we have heat capacity versus specific heat capacity. So the heat capacity is the amount of energy required to raise an object's temperature by 1 degree Celsius. So this is for the entire object or the entire system. So it doesn't include mass, which means the units for heat capacity are going to be joules per Kelvin or joules per degree Celsius. So it's just the total amount of energy required to raise the object's temperature by 1 degree. Specific heat capacity, which is what we use more often in chemistry, this is also an amount of energy, but it's the amount to raise 1 gram of substance by 1 degree Celsius. I wrote the word energy twice. Sorry. So specific heat capacity is the amount of energy required to raise one gram you're taking 1 gram of substance and raising its temperature by 1 degree Celsius, which means the units for specific heat capacity are joules per gram Kelvin or joules per gram degree Celsius. So if you see grams in the unit, that means it's a specific heat capacity, which means you need to take into account the mass of the substance that you're considering. If it's just heat capacity, it's just going to be joules per Kelvin or joules per degree Celsius. You don't need to worry about mass that is sort of subsumed into that quantity. So that first one's not so important for this problem. We're just calculating specific heat here, but we will see that on the next one, so I want to get that sort of misconception out of the way first. So here we're determining the heat capacity of, or the specific heat capacity of an alloy, if we're being real precise with terminology. So when we do these types of problems here, what we have to remember is that our object is placed into a calorimeter, and the heat that is either lost or gained by the system, which is our object, is equal to the minus heat term for the surroundings. So in a calorimeter problem, your system is whatever you're studying, your surroundings is the calorimeter itself, and that's going to be absorbing or delivering all the heat to your system. So that's sort of the main equation here, which means in the context of this problem, the heat for our alloy, Q, the Q term for the unknown object, is equal to minus Q for the calorimeter. Alright, so we have this equality here, and we're going to use, for both of these heats, we're going to use MC delta T. So the mass of the alloy times its heat capacity, or specific heat capacity, times its change in temperature is equal to the negative of that quantity for the water, for the calorimeter, which is the mass, in this case, of water. So in our calorimeter, in this case, it's filled with water. We're only told anything about the water. We have 50 grams of water. We have a heat capacity for water. We don't know anything about the calorimeter itself, so if that's the case, we assume that the water is absorbing all the heat, and we're going to use its mass times its specific heat capacity times its change in temperature. Okay? So most of these terms are given to us. The mass of our alloy, the mass of our water. We have temperature values that we can use to find delta T, which we'll do in a second, and the heat capacity of water is given. So the only unknown here is our heat capacity of our alloy, which is what we're solving for. Alright, so the delta T terms, for a calorimetry problem like this, the delta T is the same for both the systems and the surroundings. That's when the heat transfer stops, is when the two have the same temperature. Delta T for the alloy, they both stop at 31.1 degrees Celsius. That's the final T for the system and the surroundings, 31.1 degrees Celsius. The initial temperature of our alloy is 93 Celsius, so it's going to be a negative delta T of minus 61.9. And then delta T for the water has the same final temperature. It's starting at a lower initial temperature, 22 Celsius. So it's going to be a positive 9.1 degrees Celsius. When you're doing problems like this, when you're measuring heat capacities, one of the, either your system or your surroundings are going to have opposite signs for delta T. One of them will be positive, one will be negative in all cases. That's how heat is transferred between the two. So finally we can plug these values in. So the mass of our alloy, we're told, is 5.23 grams. The heat capacity of the alloys are unknown that we're solving for. Its delta T is minus 61.9, which we can also write in terms of Kelvin. For delta T, remember, Kelvin and degrees Celsius are interchangeable because the units are the same size, so the difference between two temperatures is the same in either Celsius or Kelvin. And then we set that equal to the negative of the mass of the water. We're told in the problem that's 56 grams. Heat capacity of water is given, and we should know this one. We'll see it all the time. And then delta T for water is 9.1. So when we do our algebra and solve for the heat capacity of the alloy, we get 6.59 joules per gram Kelvin. Okay. As we saw in class, there is a general equation you can write for these types of problems if you want. The heat capacity is equal to minus MC delta T for the water divided by the mass of your object, we'll call that X, times its delta T. So this is sort of a general equation, but it comes from just setting the two heat terms equal to each other and opposite in sign. So this is what we get for the heat capacity of our alloy, and this is a pretty standard calorimetry problem we want to become familiar with. Now the next type of calorimetry problem we'll do is determining enthalpy change. So here we have a calorimeter with, there should be a 1 there, I keep copying these questions wrong. The heat capacity of a bond calorimeter is found to be 5.68 kilojoules per degree Celsius. So what we see here is an example where we're just given the total heat capacity, it doesn't include the mass, and often for bomb calorimetry or constant volume calorimetry problems, this is what you'll see. You'll be given a total heat capacity, and what we're doing here is we're burning glucose, 1.652 grams, and the temperature increases from 24.56 to 29.1 degrees Celsius. Calculate delta H for the following reaction. So in these types of problems, it's a multi-step process. So first we're going to determine the heat for the calorimeter, which is just, in this case, the heat capacity times delta T. So the heat capacity for our calorimeter is 5.68 joules per degree Celsius, and then delta T is the final temperature, which is 29.1 minus the initial temperature, 24.56, which is 4.54 degrees Celsius. Alright, so if we take this heat capacity, multiply it by delta T, that means the heat for our calorimeter, the heat that is absorbed by the calorimeter, is 25.8 kilojoules using the units that are given to us. Alright, that's the heat for our calorimeter, which means that the heat for our reaction is equal to the negative of that, which is minus 25.8 kilojoules. Now what we should be aware of, though, is that this is the heat that is released, or the enthalpy change for the reaction when we burn 1.652 grams of glucose. So this is the amount of heat for that specific amount of substance, but what we're interested in is delta H for the reaction, which has a coefficient of 1 in front of glucose. We want to determine how much heat is released per mole. So for this we need to find, so our delta H for this reaction is equal to the heat of the reaction that we measured from the calorimeter divided by the moles of glucose. So we will normalize this per 1 mole of glucose, which is the coefficient that we have in the balanced reaction. So we're going to put this value in, 25 minus 25.8 kilojoules. We're going to divide that by the moles of glucose. So here the moles of glucose is just, we convert mass into moles. 1.652 grams. One mole. Now, we didn't give you the molar mass here, but we can calculate that quite easily. Is 180. We're out of room. 180.2 grams. The molar mass of glucose is 180.2 grams per mole. So when we convert the mass amount into moles, we get 0.00867. Guess we should do the correct number, so 8668 moles. So if we divide the heat from this reaction by the moles of glucose, the heat for this reaction per mole of glucose is 2976 kilojoules. Alright, so this is the amount of heat that would be released. It should be a negative number because it's an exothermic reaction. So our delta H for the reaction is minus 2976 kilojoules, and that represents the amount of heat released when 1 mole of glucose burns. Alright, so that's how we do calorimetry problem for determining delta H. It's always using MC delta T, or in this case just the heat capacity times delta T, to figure out the heat for the reaction, but then we have to normalize that per mole of substance to get it to correspond to the coefficients in our balanced reaction, which are in terms of moles. Alright, so then this problem here is one I didn't really cover in class, partly because of time, partly because your book doesn't go over it, but this is what's called a thermochemical equation, and what we're doing in this problem is using delta H as sort of a stoichiometric conversion factor, something we haven't seen yet. So we're given the heat of combustion for carbon plus oxygen to make CO2, simple 1-to-1-to-1 reaction, and this delta H is minus 393 kilojoules. And we want to know if 127 kilojoules of heat is needed, how much carbon must be consumed. So if we want to do this, we're just sort of setting up a stoichiometry problem. The mass of carbon, we're looking for the mass of carbon that's required to produce 127 kilojoules of heat. So if we want 127 kilojoules, we know from our balanced thermochemical equation that for every mole of carbon that's burned, so we have a coefficient of 1 in front of carbon, so that means 1 mole of carbon burns, that gives us 393 kilojoules. So for every mole of carbon, we produce 393 kilojoules. And now we just need to convert that into mass of carbon. So when we multiply this across, we would have to burn 3.88 grams of carbon to produce 127 kilojoules of heat. So we didn't talk about this in class, but it's in my mind a pretty simple extension of stoichiometry. If you know how much heat is released or absorbed by a chemical reaction per mole of substance from the coefficients, then we can use that as a conversion factor as we did here. Alright, and finally the last two I want to go over are Hess's law and then a related topic, which is using delta H of formation. Okay, so here we have this reaction, NaCl going to N2 plus O2 plus Cl2. So we're decomposing this into its elements. We want to know the heat of reaction given the following set of thermochemical equations. So we'll label these 1 and 2. Alright, so we want to look at our overall reaction. So our overall reaction has 1/2 N2 and 1/2 O2 as products. This first equation here has 1 N2 and 1 O2 as reactants. So if we take the first equation and reverse it and multiply the coefficients by 1/2, that should give us a chemical equation that has 1/2 O2 and 1/2 N2 as products. So if we do this, we're gonna flip the reaction and we're going to divide the coefficients by 2, so we get NO gas going to 1/2 N2 plus 1/2 O2. So that gives us 1/2 N2 and 1/2 O2 as products, which is what we want once we add the two together. So again, what we're doing here is we're going to figure out a way to add these two equations together to get our overall reaction. And then the delta H for this first step here is going to be minus 1/2 times delta H1, because we flipped the reaction and we divided the coefficients by 2. So 180.6 times 0.5 times negative 0.5 is going to be minus 90.3 kilojoules. Okay, so the unmodified equation 1 has a delta H of positive 180.6. If we reverse the reaction, that gives us a negative delta H, and then we take the coefficients and halve them, that gives us half of that value, so that's how we get minus 90.3. And then for the second equation, we see that we need NaCl as a reactant, but it's on the product side of our second equation. Our overall reaction has NaCl as a reactant. We also need 1/2 Cl2 as a product, so we're just going to flip equation 2. That will also allow us to cancel out NO. So if we flip equation 2, we get NaCl going to NO plus 1/2 Cl2. So the delta H for this is just going to be the negative of the second delta H, which is 38.6 kilojoules. So we flip the second reaction, that just flips the sign of delta H. So now when we add the two chemical equations together, we have, on the reactant side, we have NO and NaCl, but this NO cancels out with an NO on the product side, so we're left with NaCl, and then on the product side we just have 1/2 N2, 1/2 O2, and 1/2 Cl2. So we have the reaction that we wanted, and then we want to get delta H, which is just the sum of these two values. The delta H for this overall reaction is 90.3 kilojoules. Sorry, minus 90.3 kilojoules. I missed my minus sign there. Plus 38.6 kilojoules. Minus 51.7, I think. Yep. Minus 51.7 kilojoules. Okay. Alright, so that's delta H for the overall reaction after we've modified the two and added them together. Alright, finally the last one, this one was by request. We want to know enthalpy change from heats of formation. There were similar types of problems like this that we had trouble with as well. So one of the challenges in these problems, as we saw with a lot of stoichiometry problems, is we might not give you the exact balanced reaction. You have to produce it yourself and balance it yourself and all those things. So that might have been part of the challenge here. So we have ethanol made by reaction of ethylene and water. So we gave you the equations or the formulas for everything. So we have C2H4 plus water. I believe that's the liquid water, not that it really matters. Going to make C2H6O. And if we look at this equation here, it looks like it's already balanced 1 to 1 to 1 to 1. So if we add H2O to C2H4, we get C2H6O. So it's a pretty simple reaction of balance. Now if we want to find the delta H for the reaction, remember that it's going to be the sum of the delta H's of formation for the products minus the sum of delta H of formation for reactants. So when we're using heats of formation, it's going to be products minus reactants, so make sure you do them in the correct order, and also keep in mind you have to put a negative sign in front of one of those. So on the reactants, on the product side, we have just C2H6O, so delta H of formation for that is given to us as minus 277.69. And actually, I'm being a little bit callous here. We also have to multiply by coefficients. The coefficients for all of these are 1. But we have to keep in mind the coefficients. So we have 1 mole of C2H6O, and its delta H is minus 277.9. I have to see what I did in class. So that value represents the formation of 1 mole. So we have to take into account the coefficients, which is a 1 in this case. Then we're going to subtract. We have 1 mole of C2H4. Its delta H of formation is positive 52.26. And then the second reactant is water. We have 1 mole of water. Its delta H of formation is given to us as minus 285.83. So when we add these up, we get minus 44.1 kilojoules is the delta H for this reaction. Alright, so again, it's not a terribly difficult equation, but we can't forget negative signs. We have to do things in the right order. Products minus reactants, or else we'll switch the sign of our answer. Okay, so that takes us to the end of this one. So if you have any questions, any additional questions, please let me know and try to address them early on, as we have more stuff to cover in the next couple weeks before the final, before the third midterm and the final exam. All right, I'll see you next time.